We're here today to answer the question, what makes EnCann different from a technical perspective? I'll do that by explaining the difference in the process steps between a traditional high-efficiency cryo-ethanol system and the EnCann system with a proprietary solvent blend. All of the thermodynamic calculations and numbers that I'm going to give you today are based around a throughput of 1,000 kilos per hour of dried biomass using the traditional solvent to biomass ratio of 1 gallon per pound, or approximately 8.3 liters of solvent per kilogram of dried biomass. The ethanol process, before it can begin, needs to chill the solvent from room temperature, or whatever their ambient storage temperature is, to generally a temperature that's about minus 40 Celsius. A very efficient process can run at minus 20 Celsius. That requires chilling 8,300 liters of ethanol from an ambient temperature that we'll call 20 degrees Celsius down to minus 20 Celsius for a delta of 40 degrees Celsius. Chilling 8,300 liters of ethanol requires approximately 190 kilowatts of energy. That's energy that you have to put in no matter what before you can even get started. The EnCann system uses a room temperature solvent, so we don't need to spend this energy. The next step is the solvent application. This is the same through either process and is generally performed by adding the solvent into a tank or mixer and then agitating the biomass in that solvent. This can be done for seconds to minutes, depending on the process that you're using. We'll consider them equivalently the same for the purposes of this discussion. Next, you have to remove the solvent from the biomass. There are multiple ways to accomplish this, but at the scales that we're talking, the most common technologies are decanter centrifuges and screw presses. Again, these are functionally equivalent for both technologies, and so we won't discuss them further. Once you've removed the solvent from your biomass, the fun really begins. Now we have a solvent stream that has cannabinoids in it and any other compounds that were in the biomass that we need to remove. These include fats and waxes, polysaccharides, sugars, chlorophylls, and other compounds, many of which have not been well studied and identified. Traditionally, the first stage of this process is referred to as winterization. It's technically a precipitation process. The winterization process is traditionally handled by chilling your solvent from whatever temperature your process runs at to below minus 40, generally as low as minus 80 if you want a faster process. This causes the undesirable compounds in the solvent to precipitate out because they're no longer substantially soluble in the solvent, and they will drop out and can be filtered through a depth filtration process. In this case, because we're discussing a cryo-ethanol process, that process does not require a winterization step if it's performed correctly. So in this case, their energy budget is 0. Because our process is run at room temperature, we do pick up a number of undesirable compounds and we'll need to filter them out. We use a specialized filtration process. If we were to do a traditional winterization process using our proprietary solvent blend, assuming we were using 8,300 liters of solvent per hour, this would require approximately 250 kilowatts of energy. However, this is an extremely inefficient process, and we've decided we don't want to do it that way. The filtration process that we use is substantially similar to a reverse osmosis system, only it's for cannabinoids and solvents. We've developed our own system based on studying reverse osmosis systems and other filtration systems on the market. This is a simplified process and instrumentation diagram of the membrane system that we are building in-house. I say this is simplified because this is designed around having only a single process loop with swappable membranes for running different processes. The larger scale system, which we will run in production, will be substantially larger and more complicated than this, but for simplicity today, we simplified it down to this. Initially, your cannabinoid-laden solvent is put into the feed tank. The material is then fed through the first pump, which boosts the pressure of the solvent and cannabinoids from approximately atmospheric pressure to about 1,000 psi. We then travel through a flow meter and a check valve and enter the process loop. We have a heat exchanger in line because this pump puts a lot of heat energy into the process. Once the process has gone through the heat exchanger and been cooled, it then moves into the membrane separation stage. What happens in here is the solvent goes through the membrane, and because of the pressures, the temperatures, and the flow rates involved, some of the material will go through the membrane and some of it will pass by. In the winterization stage, the material that goes through the membrane is the solvents and the cannabinoids, and that goes through this and comes out as permeate. The remaining fats and waxes still left in some solvent stay in the process loop where they are recirculated. The initial feed pump only supplies enough solvent and material to the process loop to replace the permeate. This pump, our circulation pump, only adds a small amount of pressure into the system, just enough to account for the losses in the piping system and the pressure drop across the membranes. This is for flow, this is for pressure. In a solvent recovery process, we do the same thing. The same process, or the same loop with a different membrane. This membrane, the permeate, would be ethanol or your other solvent in pure form, with your cannabinoids and another fraction of your solvent remaining in the process loop. We've determined that with solvent recovery, we can, through changing the operational parameters of the system, we can choose to send the terpenes either into the permeate stream or leave them in the process loop. This allows us to recover a nearly complete terpene fraction, which we can then reintroduce into the finished products, or we can sell as a second value-added product. And that is why we have two additional stages of membranes. One would be for solvent recovery, and one would be for our terpene recovery. We also have designed a clean-in-place system for this, so that between each batch and at the end of each day, we can flush and clean the entire system so that we know, without a shadow of a doubt, that this machine is clean and ready for the next batch. And if there were any contaminants in the first batch, that there won't be any left in this one or in the next one. The winterization stage and the solvent recovery stage for EnCann require approximately 15 to 20 kilowatts each. To put that into context, the ethanol process that we're also comparing this to, for a traditional solvent recovery method where they're using a falling film evaporator or other traditional evaporative methods, will use approximately 3,600 kilowatts of energy. That's 3.6 megawatts of energy. Once we've gone through winterization and solvent recovery, we then need to decarboxylate the resulting process stream. Decarboxylation is where we take CBDA and turn it into CBD. We do this through heat. This process is similar for both extraction methods, and so we'll consider them substantially the same for this. If our desired end product is CBD isolate, which is EnCann's initial large volume wholesale product, the ethanol extractor will need to distill their resulting process stream. Their crude oil will not effectively isolate efficiently. That means that it needs to be distilled. This process can take between 1 to 8 hours, and distillation equipment is very expensive. The EnCann system, because of a proprietary solvent blend, does not require distillation prior to isolation. We can use a single solvent for extraction all the way to isolate. So in this case, we don't use any energy at all. Finally, we have our process stream that's ready for isolation. The ethanol extractors will take the distilled product and dissolve it in a preferential solvent, generally pentane, heptane, or hexane, but others are applicable in this application. And then they will chill that solvent either slowly or fast, depending on their operational parameters, until they have precipitated most of the CBD from the input stream. This is then separated through a traditional filtration process. This can be done through depth filtration at the small scale, or centrifugal or other mechanical methods at the large scale. You now have a purified product. We have now converted 1,000 kilos of dried hemp biomass into CBD isolate. The EnCann system has done this with approximately 250 kilowatts of total energy consumption, and the ethanol extractors have used about 4,000. To put that into context, the EnCann system, if using natural gas to power all of our machines, would require a 1-inch pipe to keep the system fed. The ethanol extractors, if using natural gas, would require a 4-inch pipe. So now we've covered the physics, the chemistry, the thermodynamics, the technical, the nuts and bolts and math of what makes our system so great. But that's not all that matters. We also have to worry about safety, about product quality, about regulatory issues. We need to be able to know for sure and be able to prove to the regulator without a shadow of a doubt that what comes out of our machine is safe. Even if, let's say, the day before we'd produced product with an input that turns out to have been contaminated with pesticides. There are a number of ways of doing this. None of them are easy. None of them are simple. None of them are cheap, unfortunately. But we've decided to do this in a way that we feel allows the most operational efficiency in our process. We've designed this to be a fully continuous system. Why does that matter? In a traditional batch system, you'll have a worker load the biomass into your extraction vessel, close it, charge it with your solvent, run your extraction process, and then remove the biomass manually, put more in, continue. One of the more difficult problems to solve that we've found is how do you, in a compliant manner, handle what is intended to be a fully continuous operation while still having batch separation and cleaning between product batches? How do you ensure that if you take some material and you run it through your system and it ends up with pesticides in it, that the next material is not going to be contaminated? This is extremely important from a product safety standpoint. It's also important from a GMP perspective. This is mandatory. You need to be able to do this if you want to play on the world stage. So we looked at the possibility of using some form of conveyor. We would use a screw auger or a disc conveyor or other method to move the biomass from our storage area and into the extraction system. Unfortunately, the cleaning process for these systems is not quick, it's not simple, and time is money, so it's not cheap. Our system requires the batch vessel to be attached to the system, and that's it. From there, the system handles the rest of the process. Instead of manually adding and removing biomass at every step, moving your solvent from the one step to the next, from extraction to solvent recovery to winterization, moving it in and out of a freezer, moving it from one side of the lab to the other. Ours is all handled by pumps and automation. We're building all of that in-house because we want this to work the way it needs to. This system that we're running on a fully continuous operation should require no more than 3, maybe 4 employees to keep it fed and keep it happy. That's 4 people for 1,000 kilos an hour of biomass. Go ask a CO2 extractor how many people they'd need to run that much.